Everybody.
Hello. Good afternoon.
So today we have Aneesh presenting, so give it up for Aneesh.
So some of you may not know, but Polymer does in fact have a 3D printer. You can find it in the tech office or in the room adjacent to it. It costs $8,000 and it's quite bad, but we do have one. And that first, if you're wondering what a 3D printer is, no fear. Basically, if you think about a normal printer, the kind you would use to print like your essay or something like that, the way that something like that would work is you would have like a nozzle that sprays ink onto a page. A 3D printer works a little bit differently. Instead of spraying something like ink, it sprays plastic filament, or it extrudes plastic filament. And it uses this filament to layer objects, so it puts the filament on top of the lower layer beneath it, and therefore that's how you're going to get those 3D objects from the printer. So it can be used for a lot of purposes. Most standard, the fairly inexpensive kinds of printers print only in plastic. So you just load up some plastic and you input a model and it'll print it for you. It can also be used to print things like sugar objects, like for example cake decorators, and high-end shops can use it. And if you have a large enough one, you can print something as big as a car in different parts, of course. So that leads us to the paper. It is called The Three-Dimensional Printing of Hierarchical Liquid Crystal Polymer Structures. And this paper the research here was carried out by a team at ETH Zurich in Switzerland. So first of all, what is the purpose of the paper? Basically, they looked at carbon fiber, which, as some of you may know, is exactly what it sounds like. It's strands of carbon that are woven together and densely packed. And this makes into flat sheets, and this is going to make a really strong structure. So if you think about planes and high-end vehicles and a lot of industrial applications, those machines and those structures are all built with carbon fiber, among other ingredients. And the reason is because it's extremely strong. It's very stiff, it's not easy to bend. It's also very light, which is good if you want to cut the weight down. But some of the problems with it, it's not recyclable. If you think about it, right, like you can't just melt down cloth. Similarly, it's not very easy to melt down or try to repurpose carbon fiber. And in addition to that, it is also difficult to mold. So in the factory, when you're trying to make this, if you screw up, then it's likely that you'll probably have to throw up the whole piece. And so you need a lot of energy to make it. On the other end of the spectrum, you have naturally derived products like wood and bone and silk. These are all biological structures, which means that they're able to adapt to the kind of environment around them, so any environmental factors will affect them. And the fibers in them, if you think about wood, for example, it has a grain. So the same way in bone and silk, the fibers or the molecules in them are arranged in a specific way, and this allows them to adapt to various environmental conditions. They are recyclable, but they're not easily manufacturable. Like, how would you manufacture wood? Doesn't really make a lot of sense. And additionally, wood is not as strong as carbon fiber, which is why you probably don't see a lot of planes being made out of wood. So the big idea on this paper is, what if we made 3D printable material using a specialized architecture that is as strong as carbon fiber, but is much more recyclable and easier to make? So some of the definitions you need to know. We start off with liquid crystal polymer. So this is in the title, and this is a type of polymer. An example is Kevlar, which is what they use in bulletproof vests. So these kinds of polymers are very strong, inert, they don't react easily, they're very heat and chemical resistant. They're also anisotropic, which we'll get to later. The Young's modulus is just a measure of something, so it's the relationship between the stiffness of a material and the strain being placed on that material. So the higher the Young's modulus, the stiffer, and the lower, the more flexible it is. The anisotropy we talked about before, basically, if you think of wood, right? If you were to take a piece of wood and try to cut against the grain, it's going to be more difficult than if you were to cut with the grain. So this is an example of anisotropy, where in a structure, you're going to have different properties based on the direction of the material, or the orientation of the material. The pneumatic domains This basically means that there are planes that are parallel, that the molecules inside those planes are parallelly arranged, but the planes themselves are not necessarily parallel to each other. So I have a figure, so we can explain that in the next slide. Thermal annealing is a metallurgy process actually, but it can also be used for plastics. So basically all it is you heat it up, you sustain that temperature for a certain amount of time, and then you cool it off. And this can give certain properties to the material depending on the material. It can make it stiffer and stronger and able to share the strain more easily among the molecules. And the final concept to know is ultimate tensile strength, which is basically if I have a material and I try to rip it apart, what is the capacity of that material not to kind of stretch out or become elastic. So the materials they did, and this is one of the really key points of the paper, is the LCP they used is called Vectra A950 from the Ticona line, and the 3D printer they use is an Ultimaker 2 Plus. This 3D printer is comparatively inexpensive in the 3D printer market. It's only around $2,000, which may seem like a lot, but when 3D printers, like our 3D printer is $8,000, and basically what this means is a fairly inexpensive printer like this one, if it can be used to print something that has similar properties to carbon fiber, the cost of manufacturing is going to be a lot lower, and anyone can do it. And also this LCP is just standard off-the-shelf LCP. It is a special material, but it is not, like, it's no special compound that they specifically developed. You can buy it if you really wanted to. So the first figure is kind of explaining how this LCP gets printed. So basically what happens is we start off with A, and this is going to be like the chemical structure of this compound, and then we go to B. So I talked about in a normal printer how you have a nozzle that sprays ink. In a 3D printer, that nozzle that releases the filament is called the extruder. So this gray mass here is called the extruder, and this yellow tube is called the filament in this case. So in B, we're zooming into the filament that we're feeding into the printer. You can see this is an example of a pneumatic domain where you have these parallel, kind of like a grain to the material where the molecules are arranged sort of parallelly. And if you look at it, right, if you look at C, you can see that each one of these, sets of parallel molecules is inside its own domain, and those domains are not necessarily parallel to each other. So you can see in this one, on the top left, right, all of the grain of the material is going to be going kind of like this way, whereas the grain of this domain is going to be going kind of at a diagonal. So that's what would be classified as a pneumatic domain. That's what they meant when they say pneumatic domain. So this nozzle is where the filament is going to come out of the 3D printer. So it gets squeezed through that nozzle as it's being heated up. And you can see this is what happens to the pneumatic domains. They shift shape such that they kind of become more organized and more parallel. And when they get printed, right, which is what happens kind of next as it's coming out, they separate out again. You can see this is not, these grains are not as parallel as they were when they were getting squished. And this is called the freezing of the pneumatic domains, when they come out and the molecules, they get set in their arrangement. And then finally, F is what we call hierarchical printing, where you have this kind of shell architecture. And that is enabled by the specific liquid crystal polymer. And then over here, G is basically showing that once these molecules are printed during that heating process, they're able to bind to each other really well, and what that allows them to do is share the strain. So if you were to put strain on one specific part of the object, one molecule isn't going to take the brunt of it, it's going to be able to share it properly. And this is just, a sample structure that was taken. Yes?
What material are we looking at right now?
Liquid crystal polymer.
Okay.
Yes.
How are you creating those bonds in G?
When it gets heated up, as it comes out. So this is what, again, we talked about hierarchical printing, and this is what we talk about. This is what that means. So A, this is an actual picture. What they did is they printed some of the filament and then they tried to rip it apart. And using a scanning electron microscope, you can see this kind of shell architecture there, where you have this inner filament, and then around it you have kind of an outer casing. And even if you look at the cross sections, you can kind of see this inner filament and an outer casing, even in the layer height. Yes.
Why is there a shell architecture again? Is that just like the nature of the filament?
Yeah, it's the way it's made. So the first experiment, there are two, is basically how do various factors affect the Young's modulus. The Young's modulus, again, being the higher the Young's modulus, the stiffer, the lower it is, the more flexible. So this is the first figure in this experiment. So you can see the Young's modulus is being measured on the left, and the ultimate tensile strength, remember it's basically kind of a measure of the strength of a materials on the right. And the black boxes represent the Young's modulus, and the triangles, the blue triangles, are the ultimate tensile strength. So what you can see here, if you kind of look at the curve formed by these two sets of points, is that the maximum Young's modulus, so the maximum stiffness and the maximum strength of the material, is going to occur when the diameter of the filament coming out of the nozzle, the extruder, is somewhere around 0.2 to 0.3. And this may seem like that doesn't make a lot of sense, because if you think about it, if you were to print something really thin versus something really thick, right, you would expect the thicker one to be stronger. But that's not how they did the test. The test here is to measure in a layer of a certain height and of a certain dimension, how does the nozzle diameter affect that strength. So the thinner nozzle diameter means that effectively there are more lines of filament. And if you think about it, right, a bundle of twigs is going to be stronger than one big thick twig, because you're able to share the weight evenly among the smaller twigs than you are in the bigger twig. So the second factor they look at is the temperature of how hot the filament coming out of the extruder is going to be. So you can see that here the graph is a little less easy to decipher. It's kind of a mess over here, where the data is fairly strewn about, and it's difficult to come to any clear conclusions about where the highest point is. But if you were trying to figure out the best compromise of the best temperature, where you get the most stiffness, you get the most strength, it would probably be somewhere in this 280 to 300 degrees Celsius range. Yes.
Why does the data go up and down in between 280 and 300?
Did they ever explain that?
Not really. They kind of just present it and say that just from the graph, this is just the best. And you can see that this it's not consistent at all here, and that could just be because of the trials they did. Like if you get that kind of data, like there's not much you can do about it. But if you look at the scale, like these are not too far apart. Like they're fairly close to each other, close enough that you could say that that range is a good temperature. So this one is the layer height. So basically, for one layer, how thick is it? If you make it thicker, what strength do you get? If you make it thinner, what strength do you get? So here you can see the curve is really easy. They basically follow the same, both the Young's modulus and the ultimate tensile strength follow kind of the same curve. So as the layer height gets thicker, right, both of them, the Young's modulus and the strength, decrease. Which again, we go back to our nozzle diameter scenario, right? A bunch of twigs is going to be a lot stronger than one big thick twig. That's the same kind of scenario here. If you have multiple thin layers, it's going to be a lot stronger than one big thick layer, because the weight can be distributed evenly. And this one is the annealing time. So we talked about annealing. You heat it up, you hold that temperature for some time, and you cool it down. So that's what is being referred to as annealing time in hours here. And here, we have horizontal and vertical extrusion. So it's a little bit different. But they are still looking at the ultimate tensile strength. So what we can see here is that at around, if you don't anneal the polymer at all, you get very little strength between the two, or comparatively little strength. The longer you anneal it, it seems that the strength on both horizontal and vertical extrusions increases significantly. So what this means is that the annealing process is very, very beneficial to this polymer's ability to distribute the load equally. Yes.
Why do you think the verticals like had less strength? Why is it so significantly less? Or is it? But yeah, like the vertical scale is like from 100 to 600, and
yeah, it could just be that the way they did these trials is that the structure of the vertical extrusion would be inherently less strong.
okay.
So the conclusions from this experiment is that the Young's modulus is going to increase, right? This is that the material is going to get stiffer as the nozzle diameter decreases. And the material is going to get stiffer, it's going to get stronger as the filament height decreases. They kind of go hand in hand with each other. And then the second part of this experiment with the temperature is that the higher printing temperature leads to the longer cooling time, obviously, and that leads to the longer freezing of the pneumatic structure. We talked about the freezing of the pneumatic structure is when those molecules come out of the extruder and they cool down and they kind of get frozen into those orientations. So when you heat up the filament more and more and more, and it takes longer and longer to cool, it's going to take a longer amount of time for those molecules to freeze into their pneumatic domain. And this is going to lead to a lower Young's modulus, right? Because now there's an increased likelihood that each of these individual molecules is like off in different directions because they've had time to settle down, and that in turn is going to lead to less strength of the molecule. And then finally, the longer the annealing leads to the greater the strength of the material, especially so horizontally than vertically. So the second, it's kind of an experiment, but it's more of a kind of like a free-for-all-ish. They've decided to build materials using this and see what they could do. So first of all, they thought they would, and this is where we talk about, the natural structures like bone and wood and silk come in. So something like, concrete maybe. It's going to be flat, or it's going to be flat, and it doesn't really have too much of a grain. Or something really smooth and flat like that. And that's what we call isotropic, where you don't really have a grain. It's very smooth and flat and consistent all the way through. And isotropic materials have the same properties no matter what orientation the molecules are going to be in. So if I took a knife and I cut this isotropic material horizontally and vertically, it'll cut the same way. It's not going to be more difficult one way or the other. Unidirectional, you can see here that it does have a grain. It has these vertical lines, but this hole in the middle, which they're using to, kind of as a hook when they try to rip the material apart, they don't really adapt to the hole. And this is a unidirectional material, which means that no matter what kind of imperfections or what kind of environmental factors there are in this material, the grain is still going to be the same. And finally, we have directional, where you have the vertical lines, but they are adapting to that hole in the wood, which is what you want, because it's able to adapt to those environmental factors, so it's able to adapt to the stress put on it. So what they did here is they basically did a stress test. They put more and more strain, and they looked to see at various levels of strain how much stress the material could take before catastrophically failing. So we look at the isotrope, it did horrendously, because when you pull it apart, if we look at this graph of where the strain was being distributed, there's a huge bulge over here, which means that we can see that that's what took the majority of the strain. It's not being distributed evenly at all. It's just being kind of lumped to a side, and obviously because you have that amount of material is not meant to take that much amount of strain, it's going to catastrophically fail a lot earlier. If we looked at the unidirectional material, this does much better. Specifically the annealed, which is this darker brown line, is a lot more stronger. But if we look at this graph, or this figure which is showing us the strain, you can see that it's fairly evenly distributed to the sides, but in this kind of column that's surrounding the hole in the material, there's very little strain on it. And again, what this means is that the strain is being distributed more evenly, but still not evenly across the whole material, which means that it's going to catastrophically fail earlier. Finally, the directional material, this is the one inspired by things like wood and bone and silk, does much better than the unidirectional and the isotropic material. You can see that it's able to, even though it's not able to withstand more strain, it's able to withstand more stress at that specific amount of strain, or able to go to more stress at that specific amount of strain. And that's explained when you look at this figure, right? You can see that there is like a little bit of purple here, which means around that hole, you know, there's some small flares of where the material, where the strain is not going to be distributed equally. But this X pattern is kind of encompassing like this whole side and this whole side, and it's going to continue down here as well, which means that the material, except for 2 spots, is basically evenly spread out among the entire material, which is very good. It means that it can withstand a lot more strain because you're not putting an undue amount of strain on one molecule. Yes?
Could you just explain what the difference between stress and strain is?
Yes, so the strain is, the tensile strain is if I, you know, took a hook here and I tried to rip it apart, and the stress is how much that can withstand before catastrophically failing. So this is some of the figures they were able to print. So this one is called an impact-resistant Bouligand type plywood arrangement structure. And the important thing about this it is a very complicated structure. It looks very complicated, and that's because it is very difficult to print normally. But and you know, while retaining the properties and while retaining those sharp edges and things like that. But with this new LCP polymer and their new techniques of, you know, annealing and things like that, they're able to print it and retain that impact absorption. And this over here is it's kind of like a prosthetic almost. It's a part that could be used in a human. And what we can see here is the same holes that we talked about in the previous experiment. These holes are meant to withstand the same amount of strain. And so this material can be used in a kind of situation like this where you have to have those holes, maybe, you know, to bolt the material to the bone, right? It'll be able to distribute the strain evenly among the whole piece, so it doesn't break while it's on your back or something like that. And this is an example, so we talked about the whole unidirectional versus directional. And this is an example of what they did to the board. They basically kind of put a hook in and they ripped it apart. And so this looks like a complete failure, right? Like you can see like the plastic is falling off and it's ripped in the middle, and it looks very bad. But if you look underneath the surface layer, you can still see that the base layer of plastic, the base layer of LCP, is still there. And what that means is that this did not catastrophically fail. It looks pretty bad, but the fact that the board was able to stay together without like snapping in half means that it was able to hold it together. Yes.
How do they judge catastrophic failure?
If it's like completely destroyed, like it's ripped apart.
But that's not ripped apart.
Right. So this is not catastrophic failure.
So why do they keep going? Why do they just keep going?
Well, if we look at this graph, right? None of these materials can really withstand anything more than 8% tensile strain.
Yeah.
But at, you know, something like 6% tensile strain, this annealed directional material has a very high stress tolerance. Like it can take, like, you know, it can take a lot of that strain in terms of how much it needs for it to break. So this is what that's showing.
Alright, so this is a really high stress.
Yes.
Alright.
And we talked about in the very beginning, carbon fiber is not recyclable. If you crash your carbon fiber car, there's very little you can do with that material besides, you know, chop it up and throw it out or something like that. So the important thing they wanted to look at with this is, was it recyclable or not? So you can see this figure, and this is the melt flow index, which kind of means is how easy it is to melt. And the higher the melt flow index, the less viscous the material is, so the more fluid. So if knowing that, right, this means that the annealed samples are very thick. If you try to melt it down, you can melt it, but it'll be very like thick and syrupy and gooey, and it won't be easy to recycle. Whereas the pellets, which is, you know, what you buy from the store, and the printed feedstock, which is printed but not annealed, are much more fluid. But you can reclaim, but because the annealed samples have so much more strength than, you know, just normally printed samples, they determined that if you were to perform a hydrolysis reaction which is you add water to kind of break apart the molecules further, and then maybe some other enzymes as well to catalyze that reaction, you can regain this amount of recyclability. So, this may look dismal, like, wow, this is really not recyclable, especially compared to the, to the same material just not printed and printed without annealing. But this figure doesn't really show that a hydrolysis reaction would be able to bring the recyclability of the annealed sample back up. Yes?
Do they try a hydrolysis reaction to prove that?
They say very little about recyclability. Like this figure, it's like, they say, with the added benefit of being recyclable, figure 8b, this is a great material. Like they do not go, like even if you look at the methods, there's like not a ton. There's very, very little about even how they tested this or how they were able to determine like that the hydrolysis reaction is helpful. So the conclusions. So basically what this means is that a commonly available printer, right, this $2,000 printer, and this commonly available off-the-shelf filament can be as strong as carbon fiber. And there's a figure which I chose not to include because it's very complicated, but it does show that the amount of strain that this material can take is very similar to that of carbon fiber. So it's as strong as carbon fiber, and it's certainly more recyclable. Like, at least you can recycle this using a hydrolysis reaction. Like, what are you going to do with broken carbon fiber? And what this shows is that you don't necessarily need these really difficult high energy, high intensity techniques to make such a strong material. And that going back to basics, kind of that biologically inspired structure is going to be really helpful, as well as the material which is forming that core shell architecture. Some of the questions that they didn't really answer, they don't really give a lot of comparisons to carbon fiber. Like there's 2 figures in which they compare it, and in addition to carbon fiber, there's like 30 other materials included in the figure. So it's very difficult to conclude, all these tests that they did, how directly the material compares to the carbon fiber. We don't know about the repairability. Carbon fiber is probably not very repairable unless you try to like patch it up. Of course, that's going to compromise the structural integrity, but we don't know the repairability of this LCP polymer either. If it cracks, can you just like take, some more liquid polymer and like fill it up? Will that change the structural integrity at all? They didn't really cover that. And finally, durability over long periods of time. The reason carbon fiber is used in things like airplanes and cars and stuff like that is it's not just a strong material, it's a strong material over a lot of continued stress. Like if you think of a plane, there's constant pressure, and a material has to be able to withstand that. Carbon fiber can, but we don't know how much stress this can take over that long period of time, and they don't really talk about that either. So, but the main takeaway from this is that you can print something really, really strong with off-the-shelf available parts, and if you know how to manipulate the filament to get it to do that. So, do you have any questions? Yes.
My first question would be on cost. You mentioned that the available printers is $2,000, but in terms of the filament and the carbon fiber, what is the relative cost using those?
I tried looking up the filament, and it kept trying to prompt me to create an account to like buy it. This filament is mostly used in industrial applications. Like for example, I believe some of like their promotional images of things like phones and things like that. LCP is, like I said, also used in Kevlar. So this particular filament is a lot of industrial applications, not necessarily for the hobby project.
Is it proprietary?
This specific one is a brand name one. It's the Vectra A950 Ticona. That's a brand name one. But there's a lot of different types of liquid crystal polymers.